Yeah, so now let's move to a different problem, which is to sort a list of numbers. Yeah, so the goal here is to sort a list in ascending order, and we'll look at a very simple algorithm first. How would you sort a hand of cards? Okay, that is the intuition for the first algorithm that we'll see. So a single card is by definition sorted, so there is nothing you need to do. So once you take a second card, you will put it before or after the first card, depending on whether it's smaller valued or higher valued. When you get the third card, you will put it in the correct position, either in between the first two cards or at the end or at the beginning. And similarly, fourth, fifth, etc. every new card that comes in, you will scan the list of your hand, and then you will insert it in the correct place. Okay, and this procedure is called insertion sort. Let's actually program this in Haskell. It's quite simple to program this intuition in Haskell. Yeah, so let me just move back to VS Code and program this, and we'll come back to the slides. Insert was the procedure that we talked about, where you scan the list that you have, and you insert the new element in the correct place. Insert is of type, for the moment I will just assume that it's all integers. You have a new integer that is coming in, and you want to insert it into a list of integers that is already sorted. Yeah, so this is important. Let me add that as a comment. Insert x into the correct place in an already sorted list. In an already sorted list L. Okay, this is what I want to say. So insert x. What if your list is the empty list? Okay, then there is no work to do. This is the first card that has come in. So you just form the singleton list formed consisting of x. If my list is y followed by y's, then you will compare your x with y. If x is less than or equal to y, then you will just put x at the very beginning. So your list is x followed by y followed by y's. Else it is x followed by it's y followed by, you will insert x in the correct place and y's. Okay, but y is already there, so it is y followed by insert of x y's. Okay, and insertion sort is nothing but saying I sort of empty list is empty list. I sort of x followed by x's, x followed by L, let us say, is insert x into I sort of L. Okay, you first sort the tail. This is recursion. So you have x followed by some list. You first sort the list using the same insertion sort, and then you insert x in the correct position in I sort of L. And this whole thing can be, of course, now that we know folds, if you want an exercise in how folds work, this is nothing but saying I sort equals fold R of insert. That's it. Insert starting with the empty list. Okay. So if my original list is empty, then I'll have the output is empty list. My original list is x followed by something, then I recursively sort the tail and then I insert x in the correct position. So this is all that needs to be said. Okay. So that's my sorting algorithm. Let's actually test whether the sorting algorithm works properly, and for that I will just recall that we had all these we had introduced randomized in an earlier lecture. So how to generate a random list. So I will just copy paste that whole thing into this file. Okay, so I have a procedure that given any given the size of a list and given some lower and upper bounds, it will produce a random list of integers in that range. So let me save this. Let's go to GHCI and first I want to try isort on some thing like 199 dot dot 1. Let's see if it works on simple things. Yeah, so you can see that it took some appreciable time, but it came back with the result. Let's try this again. Okay, this time it came back quickly. Let's try 1099 all the way down till 1. Okay, this was fine. It actually sorts it, as you can see. I can try for some random list excess of size 100, let's say, with lower and upper bounds minus 100 and plus 300, let's say. So this excess is actually a truly random list, some produced randomly. Now I will try isort of excess. Yeah, this also gets sorted, as you can see, and there are repetitions, etc. These are all handled smoothly, right? Minus 100, minus 100, minus 99, and so on, all the way till minus 1, and then 10, and then yeah. So the sorting algorithm works. The intuition is very clear, right? You first have a procedure insert that inserts an element at the correct place of an already sorted list, and then insertion sort is nothing but sorting the tail and inserting the first element in the correct place of the sorted tail. Okay, so let's now compute the running time. So T of n is order of n for insert. That's because insert x in y colon y is worst case it will depend on you will make a recursive call insert x in y's, okay, and inserting x in y is might necessitate another recursive call to insert x in the tail of y's and so on, but ultimately you will end up with the empty list, and then you will create the singleton list x, okay. So worst case you would traverse the entire list, but if you are lucky you might end this whole thing in one step, because your element is even less than even the first element in the list, okay. But worst case time is n plus 1 steps or some such. So order n is the time complexity of insert. For insertion sort, this is the algorithm, and or alternatively you could just say fold R insert empty list. The recurrence now is to sort a list of length n, I have to sort the tail which is of length n minus 1, and then I have to insert the first element in that list which is order n time. Let's make it concrete, and instead of calling it order n time, let's call it 5n, let's say. But if you expand this, you will get order n squared, right? Because T of n is T of n minus 1 plus, as I said, 5n, but that is nothing but T of n minus 2, in fact, let's just be generous and say 10n. T of n is less than or equal to T of n minus 1 plus 10n. But this will be less than or equal to T of n minus 2 plus 10 into n minus 1 plus 10n, which will be less than or equal to T of n minus 3 plus 10 into n minus 2 plus 10 into n minus 1 plus 10n and so on and so forth till you reach a point where you say t of 0 plus 10 times 1 plus 10 times 2 plus 10 times 3 plus dot 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 plus 10n, and this is nothing but 10 into n plus 1 by 2, which is still order n squared, right, because 10 is your constant. You can have some other constants and you will know that eventually let us say 20 n squared, even 20 n squared will be greater than or equal to this thing on the left. Okay. Okay. So insertion sort takes time, order n squared, okay, the number of steps. Can we do better is the question. Yeah, so earlier in insertion sort we actually did it recursively. When we do the recursion, we divided the task into one smaller task, reduce the task in insertion sort reduce sorting to sorting x's and insert of x into sort x's. Okay, that's one way, but actually you could try to y sort. So to sort a list of length n, you will sort a list of length n minus 1 and then do something. You can actually do better if you divide the task more equally. Okay, you actually do two subtasks. Here the subtask for I sort of x colon x's is I sort of x's. The subtask is on a list of length 1 less than the original list, but you could consider dividing having not one subtask but two subtasks, but both of which are of much smaller size. In fact, that is what we will try to do here. You will divide the list into two equal parts, okay, and so maybe if you have a list like this, you will cut it in two halves, take the first part and the second part, separately sort the left and right half recursively, and then merge the two sorted halves to get the full list sorted. Okay, so this is the strategy: divide list into two halves, as we say, sort second half, sort first half, sort second half, and then merge the two lists. Okay, now merge is the earlier we had insert, now we have merge. So given two sorted lists x's and y's, merge into one sorted list z's, and you can imagine that suppose you have two queues, one is a queue consisting of girls, another is a queue consisting of boys. Both queues are sorted by height. How would you merge the two queues in one? Okay, you have one queue, but it should still be sorted by height. Okay, what would you do? You would compare the first girl and the first boy. If the boy is shorter, you will make the boy the head of the merged queue. The girl is shorter, you will make the girl the head of the merged queue, and then what do? You will compare the new first persons in each queue, right? Maybe the girl was put in the merged head, the head of the merged queue. Now there will be the next girl, you compare the next girl with the first boy, or if the boy was put, you will compare the next boy with the first girl, and you just continue this till one of the queue is completely empty, till one of the queues is completely empty. So compare the first elements of x's and y's, move it into z's, repeat until all elements in x's and y's are processed. So this is really the intuition. So just think of having two sorted queues sorted by height and merging them into one queue sorted by height again. Here is an example: merge of 22, 32, 43, 78 and 13, 57, 63, 91. As you can see, both these lists are sorted, and I want a full sorted one, and I want a merged list which is sorted. So let us compare. you will compare 22 and 13, and 13 is shorter, so 13 goes into the Z's queue, and the rest of the Z's will be made up by merge of 22, 32, 43, 78 and 57, 63, 91. Now once again you compare 22 with 57, 22 is smaller, so this goes here. Now you are left with 32, 43, 78, so you compare 32 with 57, 32 is smaller, so you have this. You are comparing 43, 78 with 57, 63, 91. 43 is shorter, so smaller, so this goes here, 78, etc. Now 57 is smaller, so 57 goes into the output queue, and you will end up comparing 78 with 63, and 63 is smaller, so 63 goes here, and you will now compare the list consisting of 78 with the list consisting of 91. 78 is smaller, so 78 goes here, and you are comparing the empty list against the list consisting of only 91. Merging the empty list with any list is just the other list, okay, so there is nothing to merge at all, so you will end up with this. So now, and finally your list is this: 13, 22, 32, 43, 57, 63, 78, 91, and as you can see, this is sorted, okay. So you have two sorted lists, and you are able to merge them and create a single sorted list consisting of elements that belong to either this list or that list, okay, good. So what is the, I said divide, for merge sort you need to divide it into two equal halves. You can actually split the list from the beginning, sort. So the list, you are given a list L, so you can do, if the length of the list is n, then you can go here, let us say this is n by 2 minus 1, okay, sorry, this is the middle, let us say. So from here to here you will sort, and from here to here you will sort, okay, and then merge the two, right. So merge the sorted halves into L, that is basically the algorithm. How do we sort the two halves? Recursively, right, using the same strategy. This is really the power of recursive algorithms, and let us see how to do this, okay. So if you want to sort 43, 32, 22, 78, 63, 57, 91, 13, so this is some random list. So I'll have to sort 43, 32, this whole thing, but what I'll do is I'll split the list in half. Here conveniently the list is of length 8, which is a power of 2, but even otherwise it doesn't matter, it will all work out. So I will split the list exactly here. So I have 43, 32, 22, 78 here, 63, 57, 91, 13 here. Now recursively I have to sort 43, 32, 22, 78, that means merging of sort of 43, 32 and sort of 22, 78, and on the other hand I have to merge sort of 63, 57, sort of 91, 13. Now sort of 43, 32 is merge of sort of 43 and sort of 32, I have this, and sorting 22, 78 is merge of sort 22, sort 78, and so on, right. I do all this. Now sorting a singleton list, you can just return that same list. So now this is merge of 43, 32, merge of 22, 78, merge of 63, 57, merge of 91, 13. If you actually follow the merge procedure, you will actually get 32, 43. Merging 43 and 22 will give you the list 32, 43. Merging 22 and 78 will give you this list. Merging 63 and 57 will give you 57, 63, and so on. And now if you merge them, I will get 22, 32, 43, 78, 13, 57, 63, 91. This was the example in the earlier slide. So if you merge this properly, you will actually get a sorted list, okay. So this is actually how you do merge sort, yeah. So you started out with this. You sort this, and then you will get 22, 32, 43, 78. You sort that, and you will get 13, 57, 63, 91, and then you merge them and you get a overall sorted list. Let's actually program this, yeah. So merge of empty list wise is just wise, merge of excess empty list is just excess. Merge of x followed by x's and y followed by y's, as I told you, compare x and y. If x is smaller, you put x as the head of the output q and you merge x's with y colon y's. Otherwise, you put y at the beginning and merge x colon x's with y's. Okay, that is merge. So, now the time taken for merge is order m plus n, where m is length of x's and n is length of y's. And one easy way to say this is that each comparison adds at least one element to the output list, either x or y, and there are totally m plus n elements in my original two. If I take the original two lists together, and they will all be sent to the output queue, one on each step. So, you will get order m plus n as the time required for merging two lists. Okay. So, merge. So, here I am expressing it as order n, where n is the length of x's plus length of y's. Okay, good. Finally, merge sort. So, sort of empty list is empty list, sort of singleton list is singleton list. Sort of x's is merge sort the front portion and sort the back portion. Okay, where front and back is split at n x's, n itself is length x's div 2. Okay, so this is the algorithm. You take your x's, split it as front and back, and then you will sort front, sort back, merge them. Okay, this is the algorithm. Let's actually program this and run this to see how it works. I will now switch to VS Code, and I will copy this from some other thing that I have written to save time. Okay, so I have written this program. Let's go to GHCA and see how it works. Let's try the same. I might not have access anymore. Let's try the same. This time I will try a list of size 1000. Okay, I have some huge list. Clearly, it's random because you see that there is 23788, 17086, some minus 599. Yeah, it's a jumbled up list. So now I will try to isort x's. Okay, m sort x's. Yeah, so you might not have seen the difference much, but m sort is quicker than isort. Actually, you can try to do isort of 10,000 9999 dot 1. You will see how slow it is. As time goes by, it gets quicker, but it is really slow. Because it has to take time 10,000 squared. Okay, we check that the time for insertion sort is order n squared. We haven't yet looked at the time complexity for merge sort. We will do that in a subsequent lecture. But if I try the same thing with m sort instead of isort, you will see that it is much quicker, right? And in fact, much of the time is taken by printing out this thing. So once again, I will try to do length of m sort of . This was very quick. Let's try isort. Yeah, you say that you can see that it takes an appreciably longer time. Okay, now I hope you've learned some basics of sorting in this lecture. We will come back and in a future lecture we will look at the time complexity of merge sort and other topics related to that. Okay, thank you.